Hi everyone! In today's video we will talk about statistical tests like t-test, ANOVA test, linear regression and how to perform them in Excel. If you're new to this channel, I'm Karina. I have transformed my career from finance to data and now I'll help others to do the same one step at a time. If you've been following me for some time, you definitely noticed change in scenery. March this year I had to move from Saudi Arabia to United Arab Emirates. Now I live in Abu Dhabi and there were some changes in my life, so I had to find a new full-time job that has a good maternity cover and insurance. Based on this phrase, you probably guessed that it is two of us in this video, and that also explains why I've been away, because last 6 months were very difficult for me physically and I just was surviving. It wasn't a good time for me to make videos. But luckily I feel much better now and hopefully I can make more videos and share my knowledge with you. While I was looking for a job, I went through different interview processes, and at one of them I was given a data set and then a test with questions based on the data set. And some questions were like, which strategy is statistically significant, what is the p-value, and that would inspire this video. All these calculations can be performed in Python, but you can also do them in Excel. So today we will talk about this Data Analysis Toolpak, how do you select data and how you interpret the results of those tests. So today we will be working with Data Analysis Toolpak, and at first you need to add it to your Excel. If you're using Excel on Mac, as I do, you need to go to Tools, and then in Tools you can select Excel add-ins, where you need to tick box next to Analysis Toolpak. You can see it is selected for me. If you're using Windows, then you go to File, click Options, then you click Add-in, and you also find Analysis Toolpak. So it should be located somewhere here, and for Mac it is in Tools. Now we have different data sets and we will start with descriptive statistics. When you perform exploratory data analysis, you often want to quickly analyze what is the maximum value, average, minimum, standard deviation. It is very easy to do in Python, and apparently it's also very easy to do in Excel, which I learned only 3 days ago, and previously I would just use formulas like max, mean to find those values, or average. But with this Data Analysis Toolpak you can get all the data very quickly. First of all, we need to go to Data tab here, and this is where our Data Analysis Toolpak located. Now let's click on it. It gives you different options. So here you can select all the tests, for example, ANOVA, correlation. You can find a t-test, that test, but at first we will look at descriptive statistics. So click OK. Now you need to select your input range. Let's select from C2 up to C51, so all C column. It asks if you have a label in the first row, if you have a header. If I select C1 to C51, in that case I had to tick this box and say that my first row is a header, but we selected C2 to C51, that's why it is unnecessary. Then you need to select output range. Similar to pivot table, you have several options, so you can create it in a new workbook, in a new worksheet, or you can select the output range where you want these statistics to be located. Let's click anywhere, let's say E3. And then you need to tick summary statistics, and there is also an option to select the confidence level for averages, but I will not select that. Let's hit OK, and this is the results. So now you can see what is the average value in our data set, standard error, median mode, what is standard deviation, skewness, minimum, maximum, sum, and count, so how many values we have. And when you perform data analysis in Python, this is usually the first step to get the stats, and now you know how to do it with one click in Excel. The next test we will look at is t-test. T-test in statistics compares the means of two groups to identify if the difference in the means is statistically significant. For example, you have two marketing strategies and you want to see if your customers spend more after the strategy A or strategy B. For example, you're doing email campaigns versus online advertising, or you're doing social media marketing versus pop-up ads in your app. In case of t-test, it's always two groups. If you have 3 or more, we will need to use ANOVA test, and we will talk about it in a couple of minutes. For example, we have this data set. This is the revenue by customers, and we compare strategy A and strategy B. Again, going to data analysis, here we need to find a t-test, and we have three options: pair, two sample or for mean, two sample assuming equal variances, and two sample assuming unequal variances. In our case, we will look at two sample assuming equal variances. Let me quickly explain to you the differences in those three t-tests. So the first one is a pair two sample for means, and in that case samples should be related. For example, you have before and after measurement, so you are running some weight loss program and you want to see if the changes in body weight were statistically significant. So in that case you use a pair two sample for means t-test. Other option, you are comparing the same customer under two plans, or the data is naturally paired. For example, it is the same user, the same store. In a business scenario, for example, we are introducing new loyalty program and we want to see how it affected customer spend. So it will be the same customers before we introduce this loyalty program and after. So it is the same people. That's why again t-test paired. And other two options, we have two sample assuming equal variances and unequal variances. As you guessed from the name, equal variances assume that both groups have the same variance. So you need to look at standard deviation, and if the groups are similar in spread, in standard deviation, we're using this type of test. And if standard deviations are different, we need to use two sample unequal variance or Welsh t-test. For example, our strategy A average value is 50, standard deviation is 5. And strategy B, we have average 60 and standard deviation 20. The standard deviations are quite different, so in that case we should use t-test assuming unequal variances. In our case, we will look at t-test two sample assuming equal variances. This test is used when our groups are independent, so they have different sets of customers, and also standard deviations are roughly the same. If you're not sure if the standard deviation is roughly the same, you can use descriptive statistic in Excel that we've just spoken about. So click OK. Now we need to select variable 1 range, add a variable 2 range. Variable 1 will be from A2 to the bottom, in my case it is A51, and variable 2 will be from B2 to B51. Then we need to select hypothesized mean difference. We will select 0. Here you are indicating if your data set, if your variable range has labels, in our case not. Again, if you selected A1 to A51 or B1 to B51, you need to tick this box. Alpha, keep it as it is our p-value. And again, we need to select output range, so it can be new workbook, new worksheet. I will just select this cell, it is up to you. Okay, this is the results of our test. And now let's read out the results. So first of all, we have data for variable 1 and variable 2. The first data point is mean or average. So what is the average spend per each of the variables or per each of the strategy? And you can see we have 48.21 versus 52.36. You can see that on average strategy B customers spent $4.17 more. Here is our variance, our spread. We do have difference in spread, but it is not extreme. If you look at observations, it means how many rows of data or how many users we have per each of the variance. So we have 50 users, so 50 customers in strategy A and 50 in strategy B. So pooled variance is a combined estimate of variance used in this test. Hypothesized mean difference was our input, so we inputted 0, and we are testing if the difference in means is 0, so meaning no difference. DEF is degrees of freedom, and it is calculated as N1 plus N2 minus 2. So 50 plus 50, which is 100, minus 2, and that's why we have 98 degrees of freedom. T-stat is the bigger in absolute terms, the stronger the difference between the groups. Then we have our p-value 1 tail and a p-value 2 tail. So p-value 2 tail, we are comparing it to 0.05, which is a classic standard p-value, and in our case it is indeed less than 0.05, meaning the result is statistically significant. And we also can look at t-critical two-tail, and t-critical is our threshold. So we are looking at our t-stat, which is 2.59, and we look at our t-critical, which is 1.98. Our t-stat, or our 2.59, is outside that range. It is outside our critical value, and it reinforces our decision to reject the null hypothesis. So after all this analysis, we are rejecting our null hypothesis, and we can see that based on our p-value, all the results are not due to chance. So we can see that strategy B leads to higher customer spend, and it's unlikely that result happened by random chance. So the other day I was asked, what's the point of even looking at those p-values if we can see the strategy B is performing better? So we are looking at the results of those tests to show that it's not due to chance, it's not random, it wasn't a fluke, that indeed this strategy performs better and the results are statistically significant to say, yeah, we need to follow strategy B. Now let's talk about ANOVA test. ANOVA stands for analysis of variance, and it is similar to t-test. However, in this case we look at 3 or more groups. So again, remember that for t-test it's always 2 groups, and if you have more than 2 groups, we have to do ANOVA test. ANOVA test is a statistical test that helps you to compare means of multiple groups to see if at least one group is significantly different from others. So in case of ANOVA test, we will not know which group performs significantly different, but we will know that it does exist there, and then you have to perform post hoc analysis. As an example, for ANOVA test, we were checking different pricing strategies. So strategy 1 was a freemium subscription, meaning that all customers have free access to the app. However, there are some paid options, and I think Duolingo, for example, has it. So to access those features, you need to pay. Option B was monthly subscription, and let's say it was $20 per month. You have no trial, you immediately sign up to the app, and then if you don't like it, you just cancel the subscription. And the third option was a yearly subscription. You do get 7 days trial, so you subscribe for 7 days trial, and then you are converted to a yearly subscription, which costs $120. So your monthly is $10, but you're paying upfront, that's why you're paying $120, and if you want to go on a monthly subscription, you have to pay $20 per month. We collected the data. We had 3 different groups of customers, so each new customer that comes to the app is assigned strategy A, B, or C and goes down that path. Then we collect data and decide which strategy performs best, and you need to run some statistical test to confirm that we should go with this strategy or another one. And at this point you can ask, how much data do you need to make a conclusion that the test is complete? Sample sizes can be different, but let's say minimum sample size for all those tests are 30-50 people per group. So if you have 3 strategies, at least you need 90 customers, so 30 people per group, 30 people for each strategy. More reliable is of course 100 to 300 per group, and the most reliable and a high confidence is around 500 to 600 customers per group. But you can imagine if your CAC, which is customer acquisition cost, if it is high, let's say it costs you $25 to acquire 1 customer, and then you need 600 customers per group, it becomes very expensive, almost impossible for a small business. In that case, of course, you can decrease your sample size and go into this more reliable group where you have at least 100, but the bare minimum is 30 customers per group. So now let's again select our ANOVA test. Again, we're going into Data tab in Data Analysis, and here we can select our ANOVA test. There are 3 options similar to t-test, we have ANOVA single factor, ANOVA two-factor with replication and without replication. So single factor ANOVA is used in 90% of the time. It has one independent variable or factor with multiple groups. So for example, we compare means across multiple groups for one condition. So we compare average spend across 3 pricing strategies. Two-factor ANOVA with replication is used when we have 2 independent variables and multiple observations for each combination. For example, you run 2 marketing campaigns across 3 regions, and for each combination you collect multiple daily sales figures. In that case, we use two-factor ANOVA with replication. Why with replication? Because you're collecting daily results, so you're replicating this data again and again. And two-factor ANOVA without replication, you have 2 independent variables, however only 1 observation per combination. For example, you have 3 products, product A, B and C, sold in US, Canada, Australia, and you have only 1 sales number. This is without replication. However, if you were tracking the data, for example, product A sales per USA on this day, on this day, on this day, you can see you have replication, and in that case you use ANOVA test with replication. In this example, we are testing 3 pricing strategies A, B and C, and want to find out if at least one of them leads to significantly different customer spendings. In that case, we are selecting ANOVA single factor. Again, we need to select our input range. I will select from A1 to C51, so select the whole data set. I selected labels in this case, I selected headers, so I have labels in the first row ticked. Alpha is our p-value, and again by default it is 0.05, and as always we need to select the output range. Click OK, and now we have our results. So again, we have it by group, by strategy, count, sum, average and variance. Again, count how many rows, how many customers we have for each of our strategy. We have 50, 50, 50. Then it's total per strategy. You can double check if you're very curious. Yes, it is the correct number. Then we have average and we have variance. At the first glance, you can see that total sales per strategy B are much higher. So we can say that the winner is strategy B. But now we need to look at the results of our ANOVA test to confirm that these differences are statistically significant. Now we have source of variation between groups and within groups. Let's look at these terms. So SS is sum of squares, DF is degrees of freedom, MS is mean square, then we have F value, P value and F critical. When we look at between groups sum of squares, it is a variability due to the difference in group means. Within group sum of squares is a variability due to randomness or individual differences within each group. Our F statistic is a ratio between group variance to within group variance. P-value helps us understand the probability that the observed differences happened by chance. F critical is the critical value for F at alpha. So what is the critical value? What is our cutoff at the alpha, which equals 0.05. So how do we look at the results? We look at our F value and then we look at our F critical, which is cutoff point, and we see that our F value is much greater than F critical. Also, we look at p-value. You can see strange number, meaning it is very little. So if we, double check that it is way less than 0.05, basically it is almost 0. Based on the results of F value and P value, we can say that the difference between strategies are statistically significant. So now we can say that at least one pricing strategy performs better than the others. So we can see that B strategy led to higher sales. So now our conclusion is that pricing strategy does impact customer spending, and strategy B leads the way with the highest average spend. But this is not the end of the test. After you've done that, you actually need to follow up with post hoc pairwise comparisons like t-test in order to identify exactly which strategies are significantly different. You've done your ANOVA test. We confirmed that yes, there is at least one group that is significantly different, and then you do t-test between groups A and B, B and C, A and C to find which group is significantly different. And the last thing we will look at is linear regression with this Data Analysis Toolpak. In our scenario, we want to understand how advertising spend affects sales, and can we predict sales based on how much we spent on our ads. So we are having this data set which has ad spend and sales. Let's create a linear regression. So again, we're going into data analysis, and here we are selecting regression. We hit OK. Now we need to select a Y range and X range. In our case, sales are Y range because we're trying to predict sales based on how much we spend on ads. Again, we are selecting from B2 to B50. Now we need to select our X range, which in our case will be from A2 to A50. Now we have some other options. Again, if your data contains headers, you need to tick this box, and then we need to select our output range. I'm happy with this D3 to D5, and we have several options of what we want to see on the results. For example, residuals, residual plots, standardized residuals, and line feed plots. So residuals is the difference between actual and predicted sales for each data point, show how much our predictions differ from their actual value, and it helps spot patterns where the model isn't performing well. Standardized residuals is residuals scaled by a standard deviation, so it helps us to identify outliers. So it matters because anything above +2 and below -2 might be unusual, and if you're following the latest news and the changes in tariffs, so for some of the stocks changes were 3 standard deviation, which is very unusual because usually the data is spread within +2, -2 standard deviations. So standardized residuals make it easier to spot potential outliers in your data. Other option is a residual plot. It's a scatter plot of residuals versus predicted values. Why it matters? It helps us to check if our model violates regression assumptions, which is linearity and homoscedasticity. We're using it to check if residuals are randomly scattered, because if there is a pattern or curve, our model might be missing something. And line feed plot, it's a scatter plot of actual versus predicted values with a regression line. It gives a visual of how well the model fits the data. Let's select all of those options. I will select 4 of them and hit OK. Okay, now you can see we have all these tables, including 2 visuals, which is a residual plot and a line feed plot. The very first table is regression statistics. The first one is multiple R, and it is a correlation between our actual and predicted sales, and it ranges from -1 to 1. So the closer to 1, the stronger the relationship, and in our case it is close to 1. The next one is R square, and it is the percent of variation in sales explained by ad spend. So in our case it is 0.89, meaning 89.3% of sales changes are explained by the model. Adjusted R square based on the number of predictors. It is useful when you have multiple variables. In our case we have only 1 variable, so you can see it is very similar to R squared. And then we have our standard error, the average prediction error in sales units. So here predictions are off by about 197 units on average. As you know, observations is a number of our observations or number of rows, number of data points. Based on this data, we can say that the model explains 89% of sales variations using ad spend. That's very strong, and our prediction error is around 197, which is actually quite low. Then we have our ANOVA table. Again, DF is degrees of freedom. Then we have sum of squares, we have mean square, we have our F statistic, and we have a significance F or P value. So if we look at our degrees of freedom for regression, it is 1, for residual is 48. It is the number of independent values that can vary in the calculation before it is locked in. For regression it is 1 because we have only one predictor, which is our ad spend. For residual it is total observation equations minus number of parameters. And in our case, it is 50 minus 2, which equals 48. And then total is obviously 1 plus 48 is 49. A sum of squares measures variations, and it is sum of squared differences from the mean. Regression sum of squares is explained variations, and residual sum of squares is unexplained variations. Explained one is how much the total variation is explained by our model by ad spend, and residual is how much variation is not explained, the leftover noise. Mean square is, as you can understand, it is the average variation per source. It is our sum of squares divided by degrees of freedom. F statistic compares the model's explained variance to the unexplained variance noise. This regression divided by residual. In our case, F statistic is very high. It is 402, and the bigger the better. So it means that the variation in sales is due to ad spend. So it's not random at all. Our significance F, again, you can see it's a strange number. If we need to compare it to our p-value, which is 0.05, and we can see that model is statistically significant. So it tells us that all these changes are not due to random chance. Now we have another table where we have different coefficients, standard error, t-stat, etc. So intercept is expected sales if ad spend 0. This value is actually not very valuable for business. It is just where the line starts. And x variable 1 is the slope of the regression line. X in our case is ad spend. So for every $1 increase in ad spend, we can expect sales increase by $2.69 on average. So that's how we read these results. Standard error helps us to show uncertainty in each coefficient, and the smaller it is, the more precise the results are. T-stat tests if each coefficient is different from 0, and of course our p-value is if it's below 0.05, the coefficient is statistically significant. And in our case, we can see that again it is almost 0, which means it is statistically significant. And now we have our lower and upper 95%. It is a confidence interval for the slope. So we are 95% confident the true effect is between $2.42 and $2.96. So if you need to make a conclusion, every dollar spent on ads leads to $2.69 more in sales, and we are 95% confident that it is somewhere between 2.42 and 2.97. Now we look at our residual outputs, predicted Y. It is what the model predicted, and residuals is the difference between actual sales and predicted sales. In case it is positive, it means that model underpredicted, and if it is negative, then our model overpredicted. At the last column, standard residuals is residuals divided by standard error, helps to spot outliers. You need to look at values that are above 2 or below -2, and that shows us some unusual behavior, for example, like it is here. And we also created two charts. One is the residual plot, one is line fit plot. On a residual plot, in ideal world, all these residuals, they should be just scattered around, and it is what we can see in this chart. Each point represents the difference between the actual and predicted sales at given ad spend level. So you can see that here residuals, and here we have our ad spend. If you can see that all your points are scattered around 0, it means that model isn't missing any pattern. You need to also look for any clear curve or funnel shape, and we don't have it. And because of that, we can make a conclusion that our model meets assumptions of linearity and has a constant variance. If you look at line fit plot, we have Y and predicted Y. So Y is our actual sales, and predicted Y is our predicted sales. And you can see that this one, X, is ad spend, and Y, as I said, it's actual sales. And you can see that actual sales are very close to predicted sales, so our model doing a great job. Of course, for this video, I generated data sets, and they look very ideal. In real life, there are a lot of things that going wrong and your predictions are very off. But in this video, I wanted to cover more what can be done in Excel and what all of those metrics mean. I hope you enjoyed this video, and I hope to see you again very soon.